Okay, so in this particular problem, we have an object that is projected with an initial velocity of some vi here in the diagram. So if you look at the left side of the screen here at the bottom, it's just vi, and that says 45 degrees above the ground. Okay, and it says here if the object reaches a maximum height of 255 meters, calculate the following: A, B, C, D, and E. So essentially, you're going to shoot something or kick something, whatever it is. It's going to follow this trajectory, and it's going to land on the ground again, and it rises 255 at the peak of the flight, and then some distance d horizontally here. All right, so let's do it. In part A, it asks us to find the initial launch speed. Okay, here we just need to find what vi is. The angle is already given to us. That's the direction, which is 45 degrees. So let's go and crack it out. So the first important thing I think you should recognize is that this is a two-dimensional problem, so you do have components. This V here is a diagonal in the northeast direction, so it has to have a component going up. So there's a VIY and also a VIX, okay? So first, break up your V's into VIX and VIY when and where appropriate. For this one, I want to do so. So for this particular diagram, I don't know what VI is, yeah. I know that I can find it though using the information in the y direction, because if you look at the diagram, the only information here is this 255 meters in the vertical direction. So delta y here from start to peak is 255 meters. And so I can just go ahead and do this. I think the quickest and easiest way to do is just use kinematics using the time independent function common form here, right? So here, instead of just saying VF square, I would just use it in the y direction. So everything has to have a subscript y. So here's VF in the y direction square minus VI in the y direction square, which is equal to 2g delta y. So you notice here, kinematics can be used. You just have to make sure you only apply information in the y and information in the x separately, and don't mix the values up, okay? All right, but we know that at the peak of the flight here, based on this diagram, at the top of the trajectory, it stops rising, so VFY is actually going to be 0, okay? Not VX, because it's still moving to the right. So a common misconception is that folks think it just stops. It only stops rising in the y direction, but VX remains the same, okay? So therefore, I'm just going to go ahead and cross this VFY out, okay? So VFY is 0 because it stops rising and then it starts to fall back down, okay? Now, I can go ahead and plug in values. G is negative 9.8. Delta Y here is 255 because I want to go from start to peak. Okay. So you notice here there's a negative sign on the left side and there's also a negative sign on the right side. I'm just going to go ahead and simplify that. The negative signs will cancel out. So 2 times 9.8 times 255 will give you 4,998. But you notice here this is VIY square, right? This is the initial velocity in the vertical component square. So to find VIY, I can just square root both sides. So if you do that correctly in your calculator, the square root of 4,998 will give you about 70.7. Okay. Now it's important here that you recognize this is not the initial velocity or initial speed, right? This is the initial in the y component. Okay. So look on the left side, right? There's 3 VI's, right? There's VI, the vector itself, and there's VIX, and there's VIY. What I just found is VI in the vertical direction. So I want to go ahead and label VIY as 70.7. Again, it's really important that you know and recognize what it is that you're calculating and not misuse them. Okay. Now, really here, this is pretty straightforward. This essentially is just a right triangle, right? You have X, Y, and the hypotenuse. Well, you know the angle is 45 because it's given. You just found out one of the sides, VIY. So to find the hypotenuse here, the vector itself, it's just basic, geometry. So here, I know that VIX is also 70.7 because it's 45 degrees. When a right triangle is 45 degrees, its adjacent and opposite must be the same magnitude, okay? Now, let's go ahead and find VI though, right? Ultimately, the part A here asks us to find the speed VI. It didn't want VIX, it didn't find VIY, it just wants to find the hypotenuse VI. So here, I'm just gonna use sine of 45 degrees. Well, sine by definition is opposite over hypotenuse. And if you look at this diagram on the left side here, again, this makes a right triangle. 45 touches the horizontal axis, so VIY is my opposite, and then VI is the hypotenuse, okay? So sine of 45 is equal to opposite, which is VIY over hypotenuse. Now, again, keep in mind the question asks us to find VI, right? So here I'm just going to do a little switch. I want to move VI up, and I'll move sine 45 degrees down to the bottom right. And then to solve for VI, I know VIY already. I already calculated VIY at 70.7. So I'm just going to go ahead and do a little plug and check. So VIY here is 70.7. And then the denominator is sine of 45. And if you simplify this on your calculator in degree mode, you'll get about 100 meters per second. So that is your VI for part A, okay? Now, if you don't want to do it this way, right, you can apply different math strategies here ultimately. So here, I can just apply Pythagorean theorem. As I stated a couple times already, this is just a right triangle. Here, we got lucked out, or we're lucky because this angle here is 45 degrees. So therefore, the opposite side must equal to the adjacent side when the right triangle is 45, right? So I can just apply Pythagorean theorem. I can say VI square, right, is equal to VIX square plus VIY square. So it's the same thing as saying C square is equal to A square plus B square. So I know VIX is 70. For this particular problem, it has to be the same as VIY because once again, the angle is 45. So I can just plug in 70.7 square plus another 70.7 squared. And then if you simplify that on your calculator, the sum of these two values will give you almost like 1,000 here, right? Excuse me, 10,000, right? 9,996. So if you square root that to find VI, once again, this is VI square. So to find VI, we square root both sides. So the square root of this, value will give you again about 100. So as you can see, there's different ways to find it. You do you. Okay. Let's go ahead and do part B, right? Actually, hold on. I can show you how to do part A using a different strategy as well. This one, it comes down to how you want to start the problem, right? So I left my right triangle here, but you notice here instead of actually telling you that the value is 70.7, I just wrote it out in terms of variable, right? So here, look at the bottom of my left side of my screen here. So here, this is set sine theta, right? Here's 45 degrees. That's your angle. Well, by definition, sine is opposite over hypotenuse again. Well, how do I find VIY? I can just simplify. I can just simply multiply both sides by VI. So I can say VIY is VI, which is the hypotenuse times sine of theta. Okay, so that's where this statement comes from. Watch what I'm circling on the screen, right? So I can say VIY is VI sine theta. Well, if you follow the same geometry, you can also say VIX is VI cosine theta because VIX is the adjacent, and adjacent corresponds to cosine, right? Now, what do I want to do with this? Well, in terms of just having an expression, right, VIY is simply the hypotenuse, which is VI times the sine of this angle. Well, I can use the same function that I did in the previous strategy. So I can just go ahead and cross VFY out as well, right? But instead of VIY squared being kept the way it is, I'm going to substitute it out, right? So the negative sign gets carried down. Well, what is VIY? Well, I just show you using geometry that you can say VIY is VI times sine of theta. So in parentheses here, I just substitute that statement. VI is just VIY is just VI times sine of theta. But then we're going to square this whole thing. But you notice here the square is outside the parentheses, so you need to distribute it to the VI and also to the sine function itself. So I'm going to do that. So therefore you get negative VI squared times sine square of theta equals 2g delta y. So the right side has really stayed the same, right? But as you can see here, we now have VI by itself, right? So this VI is not VIY. We started with VIY, but then we substituted out for VI and sine. So now I just have VI, which I can now solve for. So to solve for VI square, I need to divide both sides by sine squared theta first, okay? And keep in mind that the g has a negative sign here, and I carry that down. But really, if you do this stuff properly, the negative signs will cancel out, okay? So I'm just going to plug values in. G is negative 9.8, delta y is positive 255 because I'm going to go from start to peak. That's going upwards, so my displacement is positive here. And now I'm going to do sine square of 45 degrees. The angle is given. And so I highlighted the two negative signs once again because they cancel out. So if you simplify the numerator, you get 4,998. And then sine square of 45 degrees would just give you a half. So if you do this division, you'll get 9996. And then once again, this is VI square. But to do that, to get vi by itself, we need to take the square root of it. So the square root of this number, which is like the previous slide, it will give you 100 meters per second, okay? So it all depends on how you see these problems and how you want to start, right? Do you want to find the component and then use geometry, or do you want to start with geometry and plug into the function itself and then call it a day? All right, let's move on to B, okay? Oh, one more. Since I have this on the screen, I thought I should point this out to you, right? Using kinematics equation, this function that I boxed in red here, if you actually just rearrange it to solve for delta y, right? So it's negative vi squared sine squared theta equals 2g delta y. To get delta y by itself, you just simply divide both sides by 2g, right? I like to point this out. This is actually your hmax function in terms of g, vi, and theta. So when a question gives you like the launch angle and it tells you what the speed is, to find out how high it goes, this is the quickest way to do it, okay? So keep this in mind. If you're watching this video, you might want to add this to your notes. So this function is only applicable to find hmax from launch position, okay? So the function is just vi squared sine squared of theta divided by 2g. The negative sign here, you can leave it out because, again, the g has a negative sign, so naturally it'll cancel out because height is a scalar anyway. All right, so I hope that's useful. Now let's do part B. Part B wants us to find the instantaneous velocity at hmax. Keep in mind, at hmax, as I stated earlier, vfy goes to 0, right? So when you shoot something up in the vertical direction by itself, it has to come to a stop before it falls down. Well, the only difference here is now this is a two-dimensional problem, but that vertical concept still apply. So at the peak here, vfy goes to 0, but vx stays constant. Okay, so keep that in mind, right? Vx is present. Don't just say v is 0. No, it's vfy that is 0, but vx still exists and it's actually the same value. So if you've seen the other videos, the acceleration in the x direction is 0, so therefore vx must stay constant throughout the whole entire flight. Okay, so we already found vix earlier, which is 70.7. So vx at the top here is also going to be 70.7. So this is a good rule of thumb to do anytime I ask you for instantaneous velocity, right? At any time, I think you should definitely write out your Pythagorean theorem. Okay, so watch my screen. At the bottom here, I just wrote v of t squared equals vx squared plus vy squared. I think this is a good rule to follow and just kind of let the diagram or the problem speaks for itself. For part B, it says it wants the instantaneous velocity at hmax. So one piece of information I do know that's true at hmax is that vy is equal to 0 because it stops rising and then it starts to fall downward in the vertical direction. So therefore, if I clean this up a little bit, it really just tells me the instantaneous velocity, you know, at the peak is just vx squared, which makes sense, right? Because vy disappears, so the only velocity component left is vx. The square symbols will cancel out, so we can just say v of t at the peak is just vx. Well, what is vx? Again, vx here, you know, is 70.7, and it stays the same throughout the whole entire problem. So in the x direction, it's super duper easy to do. All right. And this is the answer for part B. Since it asks for instantaneous velocity, I just put a plus sign there for you because in this diagram, the object is moving up to the right and then right down. Okay. So the whole time though, it's moving to the right. So V is positive 70 point. Oh, I don't know why I put a 0.9 there. Excuse me. That should be a 0.7. So I'm gonna fix that real quick. Okay. All right. Now let's do part C. Okay. Part C asks you to find the total time of flight. Okay, so for this particular problem or this particular part, to find the time of flight, I'm just going to start with my acceleration function. Acceleration is just a change in velocity over a change in time, but it asks for the time of flight. So I'm just going to move the delta t to the top left and move the g down. So just do algebra at this point. All right. So now that I have an expression for t, I can just plug values in. So the first strategy I'm going to do is I'm just going to look at the time going to the peak. Once I know that, due to symmetry for this problem, I can just multiply it by 2, right? So be careful. For this particular diagram, it starts at the ground level. It also lands at the ground level. So the time going up is equal to the time going down because it's symmetrical. All right. So VF here, once again, is 0, or VFY is 0. And VIY we already calculated earlier, which is 70.7, and the negative sign gets carried over. VIY itself, though, is 70.7, and the two negative signs will cancel out. So therefore, if you find this correctly, the time that it takes to rise to the peak is 7.21 seconds. However, that's not our answer though, right? It says the total time of flight. So I already found the time going up to the peak. So therefore, all I have to do is multiply this value by 2 because the time coming down is also another 7.21 seconds. So the total time for this particular part is 14.42 seconds. Okay, I hope that makes sense. So I just broke it up into two parts. The time up, once I find that, multiply by 2 because, well, it lands to the same level. Now, the other way to do it without having to multiply by 2 and stuff like that is to just use your displacement function, right? Your vertical displacement is the initial velocity in the y direction. So again, as you practice, make sure you're not sloppy about VI. There's VI itself, there's VIX, and there's VIY, right? The fact that I'm writing delta y here should trigger that you need to use VI in the y direction. So if as long as you're focused on the directions for these types of problem and plug in the right values, you should be okay. All right. And then, so from here, really, I can just set this, right? Well, what's my displacement? For the whole entire motion, it started on the ground, it went up, but then it also came back to the ground. So delta y here is equal to 0. Oh, what's my VIY, right? It's 70.7, right? Okay. So we already found that on the diagram here earlier. VIY is 70.7. Well, what's my t? I don't know what that is. G is giving us negative 9.8, right? So you notice here you have a t and a t square. Well, what I can do is I can factor out one of the t's, right? This has a t, this has a t square. So I can factor out a t. So therefore the 70.7 has no more t, right? And then the 1/2 times negative 9.8 just has a t, right? Because I factor out one of the t's. From here, I can really just divide both sides by t. So 0 divided by t is just 0. I just carry the rest of the statement down. So all you have to do is simplify. So 1/2 times negative 9.8 is negative 4.9. Adding a negative is like subtracting a positive here. So as you can see, the only term missing here is just t. So I'm just going to go ahead and move the negative 4.9 to the left side. It's negative, so when you move it, it changes sign, becomes positive. So therefore now, to find t, we can just divide both sides by 4.9. So if you do that correctly, 70.7 divided by 4.9 gives you 14.43 seconds. As you can see, it's pretty much the same, right? Here it says 14.42 seconds. Here it says 14.43. Keep in mind there are decimals involved here, so don't trip. To me, it's the same answer. All right. Let's go ahead and do D. All right. To do D, it wants you to find the instantaneous velocity at 2.2 seconds. So not drawing a scale here. Well, the time here, watch my cursor, right? It starts at 0. And then, time clicks. So at 2.2 seconds, it's on its way up. Okay. I know that because it took, like 7 seconds to stop rising and then fall back down. So 2.2 seconds falls in between 0 and 7 seconds. So I'm just going to put the velocity at 2.2 somewhere around here just for the sake of, teaching how to solve a problem. Okay. So not to scale. So here's v of t. Well, to find v of t, I need to find vx and also vy, right? So, but Vx is super easy because it's 70.7. It doesn't change. Once you find it, it doesn't change, right? The only thing I do need to find is Vy. Well, how do I find Vy at 2.2 seconds? Light work. Just use your kinemax equation, okay? So as I said earlier, a good rule of thumb is when you're trying to find these V's, just use Pythagorean theorem, right? So here, Vt squared is equal to Vx squared plus Vy squared. Well, Vx is, once again, it's already calculated for us, 70.7. The only thing I don't know here is my Vy, right? I know my VIY was 70.7, but 2 seconds later, I know that the value, gets smaller and smaller, right? So I can just use Vf is equal to GT plus VIY. Okay, this comes from your average acceleration equation. Well, I need to find Vfy at 2.2 seconds. So G is given, right? T we know is 2.2. VIY we know is positive, 70.7. So I'm just going to plug and check here, right? So negative 9.8, T is 2.2, and then VI once again is 70.7. Or VIY, again, make sure you plug in the right value, right? Don't just put VI here. It has to be VIY because this is VFY. So if you clean this up a little bit, so at 2 seconds, VF in the Y direction is 49.14, right? So it started off at 70.7 and then it got slower by 9.8. For every second it got slower by another 9.8, and then there's a 0.2 in here. So this answer is reasonable, right? 49.14 is your vertical velocity at 2.2 seconds. So I just placed it here for you, okay? Now once you have two sides to a triangle, just plug it in, right? So I'm just going to carry this Pythagorean theorem statement down. The only thing I was holding back is Vy at 2.2 second, and I just found Vy at 2.2 second just using, again, basic kinematics here. So Vy got substituted out for 49.14. Don't forget this is Pythagorean theorem, so make sure you square these terms, and then once you do that, the whole right side is 7,413.23 here, and then we need to square root this because ultimately we need to find V of t, right? But this is V of t squared, so square root both sides. So if you square root that, you'll get 86.1 meters per second. However, you're not done yet, right? Velocity is a vector, so we just found the magnitude. We just found 86.1 as the actual length of the hypotenuse or the vector itself. However, velocity is a vector, so you need to give a direction. So watch the left side of the screen, right? I just put theta, and theta here touches the x-axis, right? So I need to find what this angle is and reference that. So to find this angle, I know in the y component here it's 49.14. I know in the x component it's 70.7, so I can just use tangent. I like tangent because I know the opposite, I know my adjacent. So tangent of theta in this particular diagram is Vy over Vx, opposite over adjacent. So to find theta, we would just do inverse tan. Okay, so here we go. This is Vy over Vx, but we already know Vy and Vx. So Vy is 49.14, Vx is 70.7. So if you punch that in your calculator in degree mode, you'll get about 34.8 degrees. So I would say that the magnitude of the velocity vector is 86.1 meters per second at 34.8 degrees northeast, because it's still pointing up and to the right, so that'd be northeast. So that would be my proper answer for part D. Okay, all right, now let's do part E. Part E wants you to find the horizontal distance. Well, the horizontal displacement function I just bust up here. Delta x is Vix times t. Once again, because this is delta x, my Vi here must be Vix, right? Not just Vi. So establish good habits of writing subscripts for two-dimensional motion. Once you get over that hump, I think you won't goof with plugging the wrong value, right? If it's delta x, it has to be Vix. All right, and that Ax is 0 because unless otherwise stated, the object only accelerates in the vertical direction due to gravity. Ax is assumed to be 0 in a vacuum, so therefore Vix here we already found earlier, which is 70.7. Well, how much time? It's just the total distance d traveled. D here in the diagram is from start to finish, so I need to use the whole entire time, right? It took 7.7 seconds to go up. No, excuse me, 7.2 seconds to go up. It also took about 7.2 seconds to come down. So the total time we found in part C was 14.42 seconds. So all you have to do is plug it in and then just plug and chug, and you should get a displacement or a distance of 1,019.5 meters. Okay, that's that. Okay, all right. Now here's the thing. Because this particular problem, right, you have to make sure you use these physics functions with the proper condition. Because this particular problem started on the ground, rose up to a certain height, and then also landed on the same level, I can find D by using the range equation, right? But it's important that you don't misuse this function, right? This range equation, as I've stated a couple times in my videos, it's only useful if your delta y is 0. So when your delta y is not 0, you cannot apply this. So physics function must be applied correctly here. Well, the range equation just said take the initial speed, you're going to square it, and then sine of 2 theta divided by g. So if you plug this in, right, Vi earlier we found is 100. Notice that this is Vi. This is not Vix, this is not Viy. This is the actual vector itself. So Vi that we found earlier was 100. So we need to go back to part A. All right, so Vi is 100. We're going to square that. And then this is sine of 2 theta. So sine 2 times 45 degrees. But in this particular case, 2 times 45 is 90. So sine of 90 degrees is just 1. So really, you would just take 100 squared divided by 9.8. And so that'll give you approximately 1,020, which, I mean, again, if you look on the left side, this is 1,019.5, right? Give ticks, decimal rounding. So as you can see, the answer plays out to be the same, okay? So just make sure you use the range equation appropriately only when delta y is 0, okay? All right, I hope that helps. Stay nerdy, don't be whack.